Welcome to PiFM at Work, and in this installment, we're going to discuss how PiFM is roughly 1 billion times more sensitive than traditional FTIR spectroscopy techniques. Now, photo-induced force microscopy is based on top of an atomic force microscopy platform. So the scanning probe platform is going to allow us to probe down into the nanoscale. And this is as you've normally seen with Nano-FTIR or AFM-IR techniques. Now, in the dynamic mode, we become much more sensitive to the forces present on the sample surface. This will allow us to get this really high spatial resolution. Now, if we use the AFM in a multimodal variety, so what we want to do is we want to look at both the first and second mechanical modes of that AFM cantilever, and we want to use the fact that we can look at one mode to examine both the topography and mechanical phase of a sample, while getting to use the other mechanical mode to sense the optical absorption that's happening on the sample. As that absorption event happens, we'll feel a small force on the end of the cantilever, and we can use that to decode where those molecules are. So here's an example of polystyrene and low-density polyethylene. You get a topographical map, you get a phase map all simultaneously, while even moreover simultaneously, we'll add the PiFM response. And if we choose one particular wave number to fire the illumination source or the laser at, we can highlight specifically the polystyrene molecule locations. If we then turn over to another wave number that will highlight the low-density polyethylene, 1466, we can highlight where that's located in the sample. Just for a comparison, the yellow dotted circle is the resolution you would have gotten with the traditional ATR, FTIR techniques. Now, PiFM has an excellent correlation with FTIR, so you can really trust the results when you want to compare those to known FTIR libraries. Here we're looking at a response from nylon. We took a sample, measured it in an ATR, FTIR, and then again in the PiFM. And you can see not only do we get the correct peak locations, but we get the correct peak ratios. And that's true for both looking at PMMA, looking at PES, and looking at this polyimide sample. Now this really allows us to have that power of the FTIR and those libraries that are available in the FTIRs to compare what we've gotten with the PiFM. So let's suppose we have an unknown, just for the sake of argument, and here we have a PVDF molecule, but we think that we don't know what that's in our sample. And we get the spectrum and we place it into an online search engine. We use Thermo Scientific, FTIRsearch.com, and we then, here's our inputted PiFM spectrum, and then we run that search and we find, indeed, we get this PVDF match with a 99.4% hit quality index. So we really get a great representation of what we expect from the FTIR libraries. So where does the PiFM really shine? It's when you want to look at a composite sample, something where at the nanoscale you have varying materials in some kind of matrix. Here we're looking at the topography of an ink toner particle. We take a bulk FTIR measurement, so we just stick that into our ATR machine and we take that measurement. And then we go in, and with the PiFM, we can choose specific locations, and maybe something about the topography draws you to that location. But we can take spectra there, and at each one of these spectral locations, you can see we get a slightly different response. And that's because in those locations, we're highlighting different materials. When the FTIR is just highlighting the ensemble. So you can see at location 1 and location 2, substantially different peak ratios and strengths, highlighting that those are materially different from in those two locations, and that they are subgroups of this composite that we're seeing in the FTIR bulk spectrum. Where PiFM really shines in that dynamic mode AFM is high resolution chemical mapping. Here we're looking at a block copolymer, polystyrene and PMMA, at a really high, or really small, if you will, pitch spacing, but really high resolution for us to resolve. We can highlight the PMMA at the 1733 wave number, the carboxyl region, or we can highlight the polystyrene at the 1493 region. If we combine those two, you can see in the combined image where they are at spatially. And if we do a little bit of a cross-section here, you can see that in some locations we're highlighting resolutions as good, if not better, than 6.5 nanometers. So we're really able to get into those small pitches and resolve where those chemicals are. And just as a comparison again, that yellow circle we saw on the previous slides, that ATR, FTIR resolution is about 3 microns across. Well beyond the size of this image. PiFM also does a really fabulous job at surface sensitivity. So it's really sensitive to just monolayers or a nanometer thick type materials. Here we're looking at a triple helix collagen. Our topography signal is basically showing us where those collagen fibrils are laying on top of a mica substrate. The amide 1 is a good absorption peak for us to look at for proteins. So we dial into that with the 1666 wave number. And you can see how nicely we highlight where those fibrils are, but not where the mica is. So really able to come down just with a nanometer tall information and resolve that out of the material. So really this is something that dynamic mode of the PiFM just does exceptionally well. Really another nice case example here is where we're looking at a polylactic acid acrylic rubber composite. And we have another video that goes into this into more detail and discusses the actual imaging done with the microscope. But here again, just to point out that high resolution capabilities of the PiFM. If we zoom in to one of these little nodules we see in the topography that are not related to the polylactic acid that we see at 1750. It's not related to the acrylic rubber we see at 1720. It is just these small individual components that are unique. And we can zoom into those, we can take a point spectrum at those locations, and as you can see, we get a completely different spectral response, highlighting that there is something different in the chemistry of that location. So while this was short, the idea was to really highlight that PiFM can give you that roughly 1 billion times increase in sensitivity. It can do it via the spatial resolution combined with that surface sensitivity or that small volume of material that's needed to get a spectral response. So we can do this at sub 10 nanometers and on monolayers. And it has that excellent correlation with the FTIR spectral libraries that so many analytical chemists are familiar with. We hope that you enjoyed this video and others in the PiFM at Work series. If you'd like to get updates for when new videos are posted, please do subscribe to Molecular Vista's YouTube channel and you'll get those notifications as soon as we upload new videos. In the future, we plan to do videos on inorganic samples with PiFM, monolayer samples, also a discussion on scattering SNOM with the VistaScope system from Molecular Vista, looking also at cross-sectional analysis and ease of use videos. So we do look forward to seeing you in the future.